Okay, so now that we've talked about the different sections of the periodic table, we're going to talk about something called the periodic trends. Those are basically properties of the elements, properties of atoms that change depending on where an atom is located on the periodic table, where an element is located. The first one that we're going to look at is atomic size. So atomic size, as you can imagine, is just basically the size of the atom. But it's a little bit more complicated than that, because how do you measure the size of an atom? If I had a basketball and I asked you how big is the basketball, you could take a ruler, you could measure the circumference, or you could measure the radius. But there's no real outer edge to an atom, right? It's, those are those orbitals where there are electrons, and the electrons are less and less likely to be found the further out from the nucleus you get, but there isn't really a strong outer edge. Therefore, we have to find really kind of interesting ways to actually measure the size of an atom. And so what we do is we bond atoms together. So we have a sample of just lithium atoms or a sample of just oxygen atoms. And then we take the distance between two nuclei, because the nuclei is where all the masses and where all the positive charges. So it's easier to figure out the distance between the nuclei. So how we measure atomic radius is we take the distance between the two nuclei and we cut it in half. So if you look at these pictures, right, here's the nuclei, here's the distance, and we cut it in half. Here's the nuclei, here's the distance, and we cut it in half. And most students believe that, just as the number of protons and electrons and neutrons goes up, the element gets bigger. And that happens in some ways, but in some ways it doesn't. If you look at this graph, you can see the atomic radii versus atomic number on the x-axis. And as we go, let's say lithium, you know how lithium is on the left-hand side of the periodic table. It's an alkali metal. As we go across the periodic table, across lithium's period, the size actually gets smaller. Neon has an atomic number, right, of 10 protons. Lithium has an atomic number of 3, but neon is much smaller than lithium. That is strange. Most students have a really hard time understanding that. So we are going to need to explain why. But then as we go down a group in the periodic table, all of these orange elements, those are the alkali metals. So lithium, sodium, potassium, rubidium, cesium, and those do all get bigger. And that's what you see when you look at this chart right here. It shows us the basic periodic trends, that as you go from left to right on the periodic table, and this of course has the transition metals removed, but as you look left to right, the atomic size decreases. And that's the strange one. As probably you would expect, as you go down the periodic table, atomic size or atomic radius increases. And so the lower left-hand corner of the periodic table is where you see the largest elements. In the upper right-hand corner, think helium, right, is right above neon. That's where you're going to find the smallest elements. I try to remember this trend by thinking he is small. The helium is a very, very, very small element. So now we need to look at why. And this is tricky to understand, of course. So we're really going to have to look deeply into atomic structure here. And remember a lot of things that we learned about in chapters 4 and chapter 5 about orbitals and electrons and the nucleus. So there's, of course, a couple different forces going on. There's the strong nuclear force inside of the nucleus, but then what's holding the electrons to the nucleus? That's that electrostatic force. The electrostatic force says that the electrons are attracted to the nucleus because the electrons are negative and the nucleus is positive. But then we also need to think about Coulomb's law, which said what makes that attraction stronger or weaker, right? Coulomb's law said if there's a greater charge, there will be a greater force of attraction, and if there's a greater distance between those particles, there will be a smaller force of attraction. So now let's look at, well, what are those things that would be attracted to each other? Well, of course, the electrons would be attracted to the nucleus. The more protons that are in the nucleus, the more attracted those electrons will be. So nuclear charge, which is symbolized by a capital letter Z, is just the number of protons in nucleus. But then, if we're looking at size, we would be looking at those outermost electrons, where those outermost electrons are. And in between those outermost electrons and the nucleus, there are electrons that are called sometimes core electrons or shielding electrons. Think of what a shield does. A shield blocks one thing from another. Shielding electrons block some of the attraction that the outer electron feels for the nucleus. So core electrons are shielding electrons, and those are all the electrons that are not valence electrons. What really determines how much attraction the outer electron feels for the nucleus is something that we call effective nuclear charge. It doesn't matter if there's 20 protons in the nucleus. If there's a lot of electrons shielding the nucleus, then that outer electron doesn't feel the whole pull of 20 protons. There's a formula for effective nuclear charge. The formula for an effective nuclear charge is the nuclear charge, the number of protons in the nucleus minus those shielding electrons. And what that is, like what is effective nuclear charge? It's what the outer electron actually, I'm going to put into quotes here, feels, because of course like an electron doesn't feel anything, but it's what it's attracted to. And this picture here helps us to understand what we're talking about. So if I look at, if I look at magnesium first, I think magnesium is on the left on your handout. If I look at magnesium and I look at this electron out here, this blue electron out here, that's the electron that's going to determine size because it's the outermost electron. It doesn't feel like it's being pulled by 12 protons, even though there are 12 protons in the nucleus, right? The 12 protons in the nucleus are shielded by the 10 core electrons. So those outermost electrons only feel like they're being pulled by 2 protons. And then if I look at chlorine, all the way on the other side of the periodic table, those outermost electrons don't feel like they're being pulled by 17 protons. They have the same shielding electrons too, but they feel like they're being pulled by 7 protons. 17 protons shielded by 10 equals 7 as that Z effective, the effective nuclear charge. So those electrons feel like they're being attracted by 7 protons. Magnesiums only feel like it's being attracted by 2. Therefore, magnesium is larger and chlorine is smaller. That is why, as you move across the periodic table, the atoms get smaller. because they have more and more protons, but the same number of shielding electrons. So the effective nuclear charge gets bigger, and those electrons are more attracted to the nucleus. They're sort of pulled in, sucked in to the nucleus. That's what's going on. That's why atomic size decreases as you go across. So let's write out, what we're going to do right now is write out a really good and well-worded answer to the question, why does atomic radius decrease as you go across a period? And we're going to, write this out very thoroughly, because on the test you're going to be asked to explain this. And there's many other periodic trends. So we're going to write it out very thoroughly once, and then you can use that as a model for your other periodic trends. So atomic radius, of course, decreases going across a period from left to right, because electrons, and this is important, when you're going from left to right, they are in the same energy level. Thus, they have the same number of shielding electrons. Same number of shielding electrons, but the number of protons in the nucleus increases. Thus, Z effective, because that would be protons minus shielding electrons, the effective nuclear charge will also increase. And according to Coulomb's law, a larger attraction occurs between particles with a larger charge difference. Thus, the outer electrons and the nucleus are more attracted to each other, and the outermost electrons are pulled closer to the nucleus, and thus the atom is smaller. We're also going to use this same reasoning for why is it harder to pull off electrons from the atoms more to the right of the periodic table. It's all about effective nuclear charge when you're going from side to side. It's a little different when we're talking about going up and down. When we're talking about going up and down, look at this model here on the picture on the right-hand side. Do you notice that there are many more energy levels? And that's the key to going up and down. Atomic radius increases going down a group from top to bottom, because electrons are in higher energy levels, which are further from the nucleus. Z effective remains the same. So generally, going down, if you actually calculate it, the number of shielding electrons increases, so does the number of protons, so the effective nuclear charge stays the same. But the attraction between the outer electron and the nucleus decreases due to Coulomb's law, which states that oppositely charged particles are less attracted to each other the further they are from each other. Thus, the outer electrons are less attracted to the nucleus, and the atom is larger. So to sum it up, as you go across, it's all about Z effective. Same shielding, but more protons. As you go up and down, there's more shielding and more protons, so Z effective remains the same. And therefore, as you go up and down, it's the other part of Coulomb's law, the distance between the particles that is making the attraction less as you go down and the atom larger as you go down. Remember, he is small, so that the upper right-hand most is where the smallest atoms are.